Thank you.
Okay, onward. Okay, got it. Okay, so I'm going to present also another story. So one starting basically from a very famous paper by Marquardt in 1966 that tried to formulate basically the question: can one hear the shape of a drum? So of course, before trying to answer this question in mathematical terms, you have to formulate this question in mathematical terms. So imagine that you have a tambourine which occupies a membrane, which occupies a region which we denote by omega, and this membrane is fixed along its boundary. So it is the boundary of the drum. So if you play this tambourine, then the displacement in the direction which is perpendicular to the plane where there is the membrane obeys the wave equation, where this constant c is some constant which depends on the physical properties of the membrane and on the tension and so on. So for example, of course, you can then set all the units in order to get rid basically of these constants c. Then there are some solutions which are somehow which have some interest, which correspond to the, let's say, to the tones that the membrane is capable to produce, which are somehow related to the sound that you hear, and are solution of the form u rho times e to the power I omega t. And to find this type of the solution, one can try to substitute this quantity u rho times e to the power I omega t into the equation. One realized that the function u and the quantity omega must satisfy this equation Laplacian u plus omega square u equal to 0. And of course, okay, this is not enough. Somehow you would like also to put some boundary condition, and since there is no displacement where the membrane is fixed, you also put the condition that u is equal to 0, so the Dirichlet condition. And of course, one thing that one would like to find is, for example, for which omega there are, say, non-trivial solution of this equation, and this actually it is simply the notion of eigenvalue. So one knows that for a region omega with satisfies certain condition, for example, in this case it is bounded by a smooth curve, that there exists only a sequence of number, lambda 1, lambda 2, lambda n, and so on, which is diverging to infinity, for which there exists, let's say, a solution, non-trivial solution to that equation. And basically, so a thing that one needs to study is the eigenvalue, let's say, problem. So for the Laplacian with Dirichlet boundary condition. And so now we try to formulate the question in mathematical terms. So imagine that we hear the same sound. So basically this means, imagine that all the eigenvalues are the same for two different regions, omega 1 and omega 2. Are these two regions congruent in the Euclidean sense? So of course, this was the question. So that, of course, one can reformulate. If you had the perfect pitch, could you find the shape of a drum or not? So are there two drums with the same sound but different shape, let's say? Okay, it took some years, and there were some partial negative and partial positive answer, let's say. And finally, in the 90s, there was the paper by Gordon Webb and Wolpert, who proved that one cannot hear the shape of a drum. So basically, there exist two drums which are non-congruent, which have the same sound. So basically, there exist two shapes. So these two shapes which are not congruent, and they are really the same sequence of eigenvalues. Okay, so this somehow is a story, but what about my research? So an aspect of my research is somehow the study of the behavior of shape functionals related to boundary value problem upon perturbation of the domains. Class perturbation that I'm interested in is, for example, regular perturbations, which are perturbations which do not modify the topology. We are just deforming the set. As I mentioned a few minutes ago, there are, say, 3 main points I'm interested in. So the first is trying to understand the regularity of this functional upon the shape. And this because one would like to apply, let's say, standard calculus, let's say, for example, in Banach spaces. Then once you know that these functionals are somehow regular, you may try to search for critical optimal shapes configuration. Try to, for example, find critical points. Basically, in there you can really apply standard tools of calculus. And then also, if you know that these shape functions are regular, sufficiently regular, then again you can apply, let's say, results that, as in, let's say, as in calculus 1, you know that if a function is differentiable, you can somehow approximate it with by means of the derivative, using the derivative. Also, in this sense, if you know that these functions are very regular, then you can try to find approximation of these shape functionals. So I'm going to state a couple of results. Let's say one which is a little bit more applied, which deals with the effective conductivity of a periodic composite, and another which is a little bit more, let's say, abstract, which deals with the eigenvalue of a differential operator. Just to have an idea of how these two type of results really appear. So here, assume that you have a periodic two-phase composite, which means that you have a composite material which is made by 2 components. One component is called the matrix, the host, which is the region that you see in white, and the other component is the inclusion, which is in gray, and these inclusions are periodically displayed in the material. So of course you have a material which is composite, and you would like to analyze this material from the point of view of the conductivity, for example, thermal conductivity. And for example, you assume that there is an ideal contact between the interface, along the interface, which means basically you have continuity both in the flux and the temperature. But of course, a thing that you like to do is to find somehow an object which represents the conductivity of this material as if it were homogeneous. And this object is called effective conductivity. Now, what we like to do is try to understand the dependence of this effective conductivity upon perturbation of the shape of this inclusion, and of also, for example, the conductivity parameters of the matrix and of the inclusion. So of course you need somehow to formulate a little bit what it means for perturbation of the inclusion. Well, a way to do that is you fix a domain, a reference domain, it is this omega, and then you somehow deform it through a diffeomorphism phi. Changing the diffeomorphism phi, you will change the shape of your inclusion. And of course, you can also somehow changing the periodicity parameters, just the size of the fundamental cell. So you can also somehow deform in some way the structure. So let's say that the type of results that one can do concern basically on the real on the analyticity, on the regularity of the map, which takes let's say the periodicity parameter Q, the diffeomorphism phi, and the conductivity of the 2 materials to this object, which is called the effective conductivity, the conductivity of a material which is somehow equivalent to this composite, but is homogeneous. And this quantity, as you see, is defined by means of some boundary value problem. Okay, just wanted to show you, but okay, I'm not really gonna devote too much time on that. So the type of results that we prove is basically that this map here depends analytically on all these parameters. So basically what you have is that the conductivity, more precisely the IG entry of the conductivity, is equal to the conductivity of the host material times a function which is real analytic. This function lambda is real analytic and depends on Q, so the periodicity parameters, the diffeomorphism, and this quantity here, which is called as a contrast parameter. So the good point is somehow that once you know that is analytic, so you have all the regularities that you want, and so you may try, for example, to apply, say, standard differential calculus in Banach spaces to, for example, find optimal configuration, or to find also approximation of this quantity here. So basically, once you have the regularity, you can apply all the instruments, all the tools that you know to get information about this quantity here. And okay, another result somehow a little bit more theoretical, instead concerning the eigenvalues of a generalization of those of that operator that we have seen, let's say, for the drum. So basically, instead of considering the Laplacian, you somehow consider this operator, which is called the Grushin operator, which is somehow a generalization, let's say, of the Laplacian, but having somehow some degeneracy, because in one direction, for example, here when the variable x is equal to 0, you have some parts which disappear. So let's say that is somehow a different differential operator, but you can really somehow try to analyze also in this case the dependence of the eigenvalues of these differential operators upon perturbation. So what we are able to prove is that the simple eigenvalues depend analytically on the shape of the domain where you are considering the problem, and instead for multiple eigenvalues, it is not, you cannot say that they depend analytically on the shape, but what you have to do is to consider symmetric function of this multiple eigenvalue. So somehow, if you have multiple eigenvalue, which means if some of those numbers in the sequence are repeated, then you need to, in order to say talk about to have some regularity results, good regularity, also differentiability, let's say, you need to consider symmetric function instead of the eigenvalue side. But really, once you have this result, you can somehow characterize also say critical shapes for these eigenvalues, which doesn't mean that you find the, let's say, the best shape, but at least you can guess. If you are interested in optimal or minimal shapes, you can guess, you have, let's say, a family where you can try to look for your minimal points, let's say. So there are somehow sometimes also different types of perforation or perturbation, which are no longer, let's say, regular perturbation, but are non-regular. So somehow they make some change in the topology. So a type of let's say perturbation, it is what we do making some small perforations. So even if they are small, they are not something that we can somehow neglect, because they can cause huge problems. And indeed, what happened is that at the end of the 80s, there was a plane flying from Denver to Philadelphia, and actually after 1 hour after the takeoff, the crew heard a long bang, and they tried to make an emergency landing, but unfortunately, before that, the right wing dropped and the plane crashed. So they tried to study the reason. What they realized is that the explosion, the accident was caused by the presence of a small cavity in the engine, which caused a crack and eventually the failure of the engine. So basically, this small cavity are considered to be the cause of crack, and so it is important to try to develop some algorithms in order to detect the presence of a small inclusion. And basically, on the study, from the study of problems in domain with small holes, for example, Maria and Kanga developed techniques to detect small perforations. But of course, somehow there are also other applications of this type of problems, which deals with, for example, the study of dilute composite materials. So you can think, for example, that instead of having a small hole, you have a small amount of a different material. So how this material may change the thermal, for example, behavior. And also other ways, the so-called topological optimization. So assume that you have a certain object, how the properties of this object will change if we remove some material. So for example, this material, this object can be lighter, so this can be good, but of course you cannot remove some material in any points. There are some points where you can remove without big problems, and other where, for example, you cannot, because it may it will be easier, for example, to crack. And let's say this means that these problems are quite important, but there is a problem that because of the difference in size between the, let's say, the small inclusion and the big domain, standard numerical methods may lead to inaccuracy and instability. And this is why we need some preliminary theoretical studies. So I will go for just to, let's say, present some application of what I did. And basically, another application that I did on a singular perturbation problem is related to the effective properties of composite materials. So in this case, okay, I'm going to be a little bit probably fast. Assume that you have, again, composite materials. In this case, what you have is that the inclusion is such that it depends on the parameter epsilon. And when epsilon is very small, this inclusion tends to be a point. So these are a situation where we are in the so-called dilute composite material. So there is one material which is a little bit is smaller compared to the other. Again, you would like to understand the effective properties of this material. Of course, you need to understand how the temperature and the flux is behaving along the interface and in these two materials. So you put, let's say, two materials, isotoping homogeneous in the host in the matrix, and you assume that the temperature and the flux satisfied some imperfect contact conditions. And this means that there is continuity on the flux, but instead there is a jump on the temperature distribution. Okay, so it's just a different type of boundary condition. Also, in this case, what you would like to do is to study the behavior of that object, the effective conductivity matrix, which represent the conductivity of this composite as if it were made by a homogeneous material. And we try, since the material depends, the geometry of the material depends on this small parameter epsilon, we try to understand the behavior of this object here when epsilon tends to 0. So this is really similar to what you do in, let's say, first courses of analysis. So you try to do an asymptotic expansion. So what we are able to prove is that this function here is a real analytic, which means that it's equal to its Taylor series. So when it's equal to its Taylor series, we know that this quantity, the conductivity matrix, can be expanded in a power series. And you also have a rule on how to compute the coefficient. So the coefficient will be related to some derivative, and you can actually, the good point is that you can compute directly this derivative. So there are also some applications to eigenvalue problems, but perhaps since my time is about to finish, I'm going to skip. I'm just going to mention that, for example, you can consider the behavior of eigenvalues in perforated domains. And what you can try to do is try to compute asymptotic formulas for these eigenvalues. So a thing that we were able to prove is, for example, to show that under vanishing assumption, you have an asymptotic formula for the eigenvalues on the perforated domain of this type. So where the nice thing is that you have explicitly the power somehow which control the difference between the eigenvalue, let's say, in the perforated domain and the domain unperturbed, and you get also some explicit characterization of the coefficient in front of that power of epsilon. And so this you can really use to also to guess some optimal location of holes in order to maximize or minimize the eigenvalue. So, okay, we saw just a small advertisement. So, okay, we collected somehow our results in a monograph that recently appeared. But I wanted to conclude my presentation, say somehow a few words about my link with Wales, so something about my past and ongoing project. So, or about 5 years ago, so I spent a couple of years in Venice with a fellowship funded by European and Welsh government, where I tried to apply these methods to composite and porous materials. And then another problem that I tried to study somehow the behavior of the solution of certain Robin problem when a parameter delta, which is inserted, let's say, in the Robin condition tends to 0. So from a mathematical point of view, what happens is that, let's say, when delta is different from 0, and for example, this function of delta, you can think like the identities, we have a linear problem. So when delta is positive, this problem here with the Neumann condition on the exterior boundary and the Robin condition in the interior boundary has a unique solution. So when delta is equal to 0, instead what happens is that you get just a Neumann problem, and the Neumann problem is somehow subject to some compatibility condition. So it may have a solution, and in that case, it has an infinite space of solution. You can just add a constant in the case, or it may have no solution. So the point that the question was at that point, what happens so to the solution when delta is positive but approaches 0? Is it what is going to converge, for example, if there are no solutions? And let's say that now I'm back to Wales in the framework of another European project, and I'm doing a secondment at Rockfield, and in collaboration with Gennady Mishuris from Venice and Martin Duxtor for Rockfield, we are trying to study what happens, let's say, to this problem when also the inclusion here tends to a point. So how these singularities, the one on the boundary data and the one, let's say, on the geometry of the domain interacts. And basically, we're trying also to analyze this both from the numerical point of view and the analytical point of view. And let's say that this problem somehow it is a kind of model, simplified model of problem which are a little bit more involved and contain transmission, nonlinear transmission condition, which appears in the study of composite material on multiphysics problems where you have, for example, two different objects, let's say, and material can be this region here in green and another inside, and so you need somehow also some relation between these two, and so you get some, let's say, transmission condition that can be very similar to this one. And so, okay, the first thing that I want to do is study this problem, and then to move to, let's say, more involved mathematical problem with some, let's say, more specific application. And that's all I wanted to say, and I thank you very much for your attention.